Well, everybody, it's good to see you all. Glad that you're all here. Looking forward to hearing what you've got in the Student Research Showcase. I hope your semester has been going well, and so I'm really looking forward to all the cool things that you're going to talk about today. Thank you. Thank you, everybody, for being here. My name is Gerardo Rivera. I'm a third-year PhD candidate at the Department of Atmospheric Sciences, currently being advised by Christina Camperedu. In this opportunity, I'm going to present a little bit of the research that we've been doing with AI climate emulators. In this case, it's just a general assessment of El Nino diversity using these kind of new state-of-the-art AI models. First, I'm going to cover what is El Nino. So El Nino is this large-scale natural shift in the tropical Pacific climate. Why is it important? It's because, as you can probably see in the figure on the left and right, we have this big warm blob of water piling up over the central eastern Pacific. I can point here, yes. So over this region, and this creates a major shift in our climate pattern. So this also happens irregularly between 2 to 7 years, and this can last for many months. So how can we quantify this? There are multiple ways to do it, but one of the easiest way to do it is we just take an average over a specific, a defined box. In this case, that red box that you have on the Central Pacific. We just take the averages of the sea surface temperature, and this somehow summarizes the variability of the state of El Nino in the tropical Pacific. As you can probably tell, it does not cover everything because, I mean, it's a fixed size pattern, and El Nino, one of the major characteristics of El Nino is that not two El Nino events are alike. So the warming patterns can be pretty different. You can have Eastern Pacific El Nino, Central Pacific El Nino. But overall, this is like a good summary or representation. We can see when this is going down, we have cool conditions over the Central Pacific. When this is going up, you have, as you can probably tell, and those are what we call extreme events or extreme El Nino. So this simplification, just by taking this index, can help us make multiple connections with different variables. One of the most important variables that people look at is precipitation. So if we correlate this index with the precipitation around the world, we can see that, as expected, over the areas where we have warm water, we have these wet and warm conditions because we have more moisture going from the ocean to the atmosphere. Whereas on the other hand, on places, so this warm water is coming from somewhere. It's taking it from the Western Pacific. So what happens is these places become dry, and we have several drought conditions in general over these regions. But you can probably tell there are impacts around the globe. This is because everybody is under the same atmosphere, so any perturbation in the atmosphere can ripple out to different locations of the world. That's what we call teleconnections. Why should we care about this? There are multiple effects in different places, and there are also effects on Hawaii's climate. So under normal conditions, we have all the corals with the algae, but under El Nino conditions, when the waters start rising up in temperature, the algae starts leaving the coral, and then the coral is left bleached. So this is a vulnerability for the corals or the marine habitats. Whereas on the land side, we have, as you can probably tell by the previous picture, Hawaii is right here on the tail. This is just significant, but it's right here on the tail when dry conditions happen. So we have less rainfall. Less rainfall means like more agricultural stress for droughts in general. So we are focused on studying this event because El Nino is basically setting the background state for any of the weather that we witness or that we see. Let's say that we have a 2-degree variation in temperature. A 2-degree variation in temperature during winter, it's not the same as a 2-degree variation during the summer. So that's basically the whole logic here. That's why we are interested in studying El Nino in general. As I mentioned previously, not two El Nino events are alike. So this is just one particular case, but I'm showcasing in general the two different patterns that we have, the Central Pacific El Nino pattern and the Eastern Pacific El Nino pattern. We're mostly interested in looking at models that can capture this diversity of El Nino. And this diversity have also different impacts. For example, if we just look at this plot, This is being made taking the index that I showed at the very beginning, which is an average of the box. And you can see you have mixed signals, like raining on the north, rain on the south. Whereas if we segregate these by the sea surface temperature anomaly patterns, we have clear segregation of signals. So having models that can represent El Nino diversity, it's very important to attribute different effects or different consequences. This is where the AI climate emulators come by. We have the numerical part of the models. They are good, but they have biases. A numerical weather model can be as good as the physics of the solver of the physical equations that are behind it as a core. In this case, the AI climate emulators are data-driven, so we can somehow bypass these biases. In this particular case, these AI emulators are being trained on the output from climate models, because the main goal is to try to recreate what a climate model does, but with AI, without any physical equation whatsoever. In this, I'm showing, for some reason, that titles are or subtitles are really small, but this is a Mudra, which is an ocean emulator, and this is the Elysium, which is a couple emulator. Couple because we have a deep learning weather prediction model, which is for the atmosphere, and we have a deep learning ocean model, which is for the ocean. So both components of the Earth are basically AI models that are communicating within each other. Whatever happens in one affects the other, and then so on. The general assessment that we're doing here is just, first, we're trying to look if they are able to reproduce the patterns that I showed before. For the Samura, which is the AI ocean emulator, we just ran a 100-year simulation with initial conditions taken from 2016. We had atmospheric forcing. Since this is a model, it needs something to be driven by. In this case, the atmospheric forcing, the atmosphere is the one that is forcing or setting the stage for the ocean. So we are just repeating the same atmospheric forcing for since 2016 to 2022 for 100 years in total. Just to compare, like these took 3 hours inference time on an A100 GPU. If we were to do the same simulation with a numerical weather prediction model, this would have taken days, if not weeks, which is the main advantage of this. But there are also some caveats, which is what we are getting at here. On the top figure, basically, what we are looking at, this is the patterns that we have for El Nino on observational data. And what we have here on the bottom, these are the patterns that we have for the AI climate emulator, this for Samura. You can probably tell there are some differences, mostly related to the intensities. And that's what we figure out. That's one of the problems of this AI emulator. The plot on the right, it's a little bit more complex, but basically what we are doing is we are doing a principal component analysis. We have PC1 and PC2. This is an easiest way to assess ENSO the diversity. Basically, what we have here on this axis, that is diagonal, you can see my mouse, we have the eastern pattern, which is the E index, and this one is the C pattern, which is the C index, which is, for some reason, is really small. The black dots represent the observations. So it means that the more dots I have over this region, which is a little bit far from the center of the axis, means I have more extreme events, which is what we're looking at. This is also what we refer as part of the ENSO diversity, that these models can capture the extreme events. And as you can see, the red dots are not along this axis. It's because these models are failing to capture extreme events. And extreme events are mostly related to out of sample, are out of sample or out of distribution in this model. So this is a particular problem that it's pretty common of all these AI emulators or AI models in general, that whenever they are being tested on out of sample inputs, they do not perform pretty well. But nevertheless, the major characteristics or major patterns are there. Then we just turn to the Elysium, which is a couple simulation, as I said. And as you can probably tell by the look at the patterns, they are not that good. Main advantage is, well, this took 12 hours to run on the A100. An equivalent simulation of 1,000 years would have taken 90 days in more than 1,000 CPUs. Same as before, this game is even worse. It's not even able to capture any of the variability that we have. The patterns are not aligning at all. So this is one of the last assessments that we make. This is part of this is all part of a manuscript that we are working on. So what we're looking at is the skewness of the distribution of the surface temperatures. Basically, this is a measurement of the asymmetry between the two different states of El Nino. We have El Nino, which is the positive phase, and La Nina, which is the negative phase. In this case, what we are looking at is, or what we are searching for is this one, which is the observations. We have positive skewness. Samudra, which is the one on the middle, for some reason the slides are really small. It's able to capture this positive skewness a little bit weaker, but the LISM is not able to capture it at all. So there's some work that needs to be done with this. There are a lot of initial conditions that can be perturbed with these models. And the main advantage of what we're trying to show here is that these models enable us to do fast experimentation compared to numerical weather models. Yeah, that's it for me. Thank you.
Hello everyone, I'm Haohan. Today I'm talking about understanding reasoning in large language.
Sorry, Haohan, I think you might need to go to the podium because the
Okay.
microphone is on top. Yeah.
Hello everyone. Today my talking topic is understanding reasoning in large language model for summarization. The question behind my topic is that quite simple. Do we really need to always ask model to think before summarization? So at the beginning, we will start from some background knowledge. Large language models are those chatbots now I think we are daily used quite often, like ChatGPT, Gemini, Cloud Group. And what is abstractive summarization? For example, you can see here, if I put a document into the chatbot and I ask it to generate a summary, so the model will generate a short version of the document in its own words. And normally the summary needs to cover the important facts in the original document. So what is the reasoning in large language model? For the general definition, it's the thinking process in those generative AIs. For example, if you input something and it will give some intermediate steps or tokens before output. Next page, we will give an example of how those model reasoning. Yeah, like the left example. If you just ask a model to give you an answer, so it's only output an answer, but sometimes it can be wrong. And if you give it a spell, like let's think step by step, then it will output some reasoning step, some intermediate step. It's just like when humans solving some math problems, if it's hard to give the final answer, just only give the final answer. You need to have a thinking process before you get the final results. Okay, so some experience have showed that if we have more thinking time or thinking tokens before get the final answer, then you can get a better performance, especially in some benchmarks like coding, problem solving, question answering, and those mathematical problems. And we don't only have the prompt to ask a model to reason. We also have some so-called large reasoning models. For example, I think now people are using GPT-5. GPT-5 and GPT-01, 03, it's all the large reasoning model. So you can say that you give the same input, but what's the difference between GPT-4 and GPT-01? The GPT-01 will, before giving the answer, it will sort for several seconds, and it will generate the answer. So normally, those researchers have used reinforced learning to train those so-called large reasoning models to perform chain of thought reasoning, and the model will get used to always think before giving an answer. So as those technical reports in OpenAI shows that normally those reasoning model can outperform those models that cannot directly reason. And you can say that in the PhD level science questions, those large reasoning model can even outperform those human experts. So nowadays in the community, there is a common belief that reasoning is a universal solution for large language models. But for summarization, it's quite different because it's not just derive some answer. It's not like math reasoning. It's need compress. Yeah. So there arise our research question that reasoning really have abstractive summarization, and how it helps summarization. So to answer this, we have built a large-scale evaluation framework. We have introduced 8 reasoning strategies that from the general domain and that can be adapted or adopted into the abstractive summarization task. And we grouped it into 3 paradigms. And we include 3 reasoning models named GPT-01, GPT-03, and GPT-5. And we have 8 data sets covering diverse domains, and it have very different lengths and formats. Okay, so here is a glance for our reasoning method. But because the time consumed, I don't have time to in detailedly introduce every method. But every paradigm, like augmentation, it means before summarization, we need to add in some extra signals, just like chain of thoughts. We ask it to think about some important intermediate steps. And like organization, it means we restructure the workflow. We ask the model to split, for example, if we have a very long document, it's very hard for a model or even human to just give the answer. But it can be easier if you ask it to read it by paragraph, or you split into several chunks. And every chunk you can give a short summary. Finally, you read every summary and you give a final summary for this very long documents. That's how organization means. And for reflective, it means ask large language model to become a self-evaluator or the self-reviser. For example, you generate several summary candidates and you can ask the large language model itself which one you think is better. Then you choose the best one to save as your final output. Okay, so we have several counterintuitive findings. The first one is that reasoning done always equals to better summaries. For example, here we have some different metrics. Some metrics like ROG and BERT score is for quality metrics, which means your summaries need to more like the human writing summaries, and your summaries need to be more fluent to read. And align score and SUMAC is faithfulness metrics, which means your summary need to be accurate, need to faithful to the original document. So as we look into those metrics, we can say that sometimes the vanilla is a standard prompting, just like the example I showed before. We just ask the model to output the final summary. So sometimes vanilla can be a quite good option because it's quite balanced, and in every metrics it can perform not best, but it's quite well. And we can say that some models like GPT-5, it can output more faithful summaries, and like those self-consistent attribute file, it can output summaries that can be more fluent. So, and from the bar chart, you can see some of those reasoning methods, it really cannot outperform the standard prompting. Okay, so the second interesting finding is that we found a trade-off between quality and faithfulness. As we have doing a linear fit, we found there is a negative correlation between the faithful matrix align score and the quality matrix BERT score. And you can say that the large reasoning model like GPT-5 can output quite faithful summaries, but it's at the cost of the quality. So like I summarize here, those large reasoning models means more accurate but less polished. Okay, so next finding is that more thinking can mean less truth. So there is a hyperparameter in the GPT-5 that's called the thinkability. So if you use minimal thinkability, it will generate very few intermediate tokens before, like those thinking tokens before outputting the final output. And as you can see there, if we put the thinkability from low to high, then the faithfulness matrix will become lower. And on the quality matrix, it doesn't really change a lot. So here we can show a case study to show how those different reasoning methods can output the summaries and how it make mistakes like hallucinations. Here is a document that from WikiHow data science that shows how to do how to cook something, and you can see the blue text that it says if you are cooking with the 2 to 3 inch is best, and if you flip the slice, stick them to blah 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 thick. Okay, but when you say the output from different method, for example, from DECO, it's a decomposition method. So you can say that it's mistakenly put 2 to 3 inches long and the uniform stick to cut attributes it to stack the slices. But if accurately, it's the cooking that need to be 2 to 3 inches long at the best. And if you sticks, it need to 1/8 thick. And you can say that the different style of different method, like GPT-5, it doesn't just output a paragraph of the summary. It's outputs several so-called point list. So normally it can be more faithful and it can be more accurate, but it's not that fluent to read. Okay, so if you are interested in more details about our method experiments and other findings, you can scan the QR code to see our paper already on the archive. Okay, so that's the all content for today. And I want to get the acknowledgement to our funding resource. And I want to end with the quote that the famous said, the truth always turns out to be simpler than you thought, just like our findings. Yeah, thank you.
Okay, good morning, all of you. My name is Abishek Samrat. I am first year PhD student at Department of Geography and Environment at the University of Hawaii. My supervisor is Sichen, and my PhD research project is to produce high resolution satellite imagery from low resolution satellite imagery. So this work is part of my larger goal. So here today I'm going to present plantation mapping as indicator of forest degradation using remote sensing and machine learning. So I divided my presentation into 5 categories: introduction, study area, method, result, and future direction. So what is plantation? Plantation is a large scale monoculture farm. It could be tree crop or it could be planted forest like timber. So it has significant environmental impact like habitat loss because it's carved out from forest. It creates fragmentation. It could lead to human wildlife conflict and also provide a space for invasive species. And it also alter regional biogeochemical cycle and hydrology. So it is carved out from forest. So like what is forest? Forest is like natural occurring tree areas having tree height more than or equal to 5 meters. So what is the benefit of forest? Forest support biodiversity. It also is great carbon sink, atmospheric carbon sink. Also provide ecosystem services for agriculture and other things. There is 2.3 million kilometer square forest loss observed between 2000 and 2012, and it's highly found in tropical climate, tropical forest climate. The major driver of forest loss is agriculture, which contribute to 90%. It also has like plantation plus cropland areas. Infrastructure, forest fire, and pest infestation is very less. So if compare with the biodiversity, carbon sequestration, ecosystems, regulatory ecosystem services, and provisional ecosystem services, among the different kind of land use land cover like plantation, forest, agroforestry, cropland, a study suggests that plantation has very low biodiversity. Carbon sequestration front, initially it has high carbon sequestration potential, but when that plantation mature, it's fall down. So yeah, it's has significant impact on natural systems. So what is the land cover land use? Land cover is like abstract representation of Earth surface. There is many type of land use land cover found across the globe, and it's very regional by regional basis. But for global study, basically a study divided into forest, plantation, agroforestry, and cropland. So I just keep it for. So there is a lot of many challenges to map plantation, forest, and other land use land cover. The some are like plantation and forest are very spectrally similar, and there in tropical region there is a frequent cloud cover found, and there is also variation in spatial resolution. So my objective here is to find effective method to delineate plantation across the ecosystem. So a study area selection was based on 3 parameters. It should have plantation, it should have ecological importance, and it should have relatively similar climate as Hawaii, because my major PhD study will be based on Hawaiian island. So I selected Golpara district of Assam in India, which is a hilly region between South Meghalaya Plateau and North Himalaya, and it's part of the it's part of the Brahmaputra floodplain. It's having area of 1800 kilometers square, which is larger than Oahu state. The major plantation found in there is rubber, tea, palm, which is recently started planting, tea, which is found in eastern side of the study area. Yeah. So to perform the analysis, we need two input data. One is like satellite data and land cover land use sample size. So land cover land use is very area specific. So in my case, I selected 10 classes. So I try to separate the different kind of plantation like forest. So there is a 4 plantation type: rubber plantation, sal and teak, the timber plantation, tea plantation, agroforestry, cropland fallow, and other classes. So satellite data, yeah. So processing satellite data, I use it's cloud computing tools, called Google Earth Engine, which use JavaScript programming language. It hosts globally planetary scale remotely sensed data, which I already have some pre-processed data set. So I choose the Sentinel-2, which is optical remote sensing data set, and it has geometrically and radiometrically corrected. I try to avoid the cloud, so I selected post-monsoon data set for 2024 and 2025, and also put the one condition: cloud, give me the data set which has less than 5% cloud cover. And after that, I got it many satellite imagery. So to convert into one, I took it the median of all of the data set. So, and signature front, I use Google Earth Engine as a base map for selecting the data set, because I am doing remotely. I supposed to visit the field to collect more data set. So signature sample was divided into like training set and validation set with the ratio of 70 and 30%. The model here I selected is SVM, support vector machine, which is tuned for the kernel type radial basis functions, and the optimal value was cost 100 and gamma 10. And after that, next step is just run the model, predicted the values, and validated the output and map was prepared in QGIS. So here is the three tools I use. Google Earth Engine for satellite image processing, Google Earth Pro for signature collection, and QGIS for map preparation. So this is the signature look like on Google Earth Pro. It's easy to differentiate between different kind of land is land cover, but spectrally they are very similar. So signature was spreaded. I tried to spread as long as possible. I randomly collected 2,600 sample size, which has T is basically have very less number of sample point because it's very concentrated on the eastern part of the region. The results suggest it's a decent accuracy. It's 92.4. However, from result it suggests that forest, rubber, tea, and agroforestry basically these all are like plantation type, and forest these all are mixing up with each others. However, plantation like sal antique plantation area is quite well. I believe it's due to its shade leaf during the winter, summertime. So might be that's the reason it is easy to differentiate. So overall percentage wise, our state area has mainly that agriculture, cropland areas. Plantation has also has significant, but it's agroforestry is also dominated. So first part is like I just area calculated based on that our study area because it's a regional study, and other is I try to combine some of the classes to produce the data which can comparable with global studies. So this is how the output look like. I still need to work on some of the part because some error is there. I will try to fix it in next step. So I am next step. I'm planning to use more machine learning models, random forest, deep learning, and other things. AI, and I will try to take as the ensemble, and yeah, I will try to solve the problem. So data I want to try more with Sentinel-1 because this is the radar data, which is all weather condition. Optical data one, if there is cloud cover, it will not work. I also want to implement add elevation data because some of the land cover type only found in certain elevations. There is a new data set available, NISA, which is recently launched by NASA and ISRO. Hope so it will improve the result. I will also include some of the during monsoon time seasonal factors in that state area. Thank you for NSF, Change Hawaii, SDSI for funding the study. Thank you.
All right, that will happen. Bear with me one moment. How do I get it to go like full like slideshow mode without? Okay.
Okay, thank you everybody for attending the event. Really appreciate it. So my name's Sam Glickman. I'm a PhD student in the Department of Mathematics here at UH Manoa, and I've been working for my fellows project with the Hawaii State Energy Office. And my presentation is titled Laying Databricks, Introducing Databricks for Data Engineering and Machine Learning in Support of Hawaii's Clean Energy Goals. Won't be too much math, just a teeny bit, so don't worry. Okay, so I want to thank the Hawai'i Data Science Institute, the Hawaii State Energy Office, and of course the University of Hawaii for supporting this work and doing such a great job of trying to bring data, clean energy to the state. Okay, so I think we all know from living here that environmental resilience in Hawaii is really important. So we have a very unique climate in the state of Hawaii with a lot of really important, unique natural resources. And Hawaii, don't quote me on this, but I watched a YouTube video that said Hawaii is the most densely populated place that is the farthest in distance from the next most densely populated place. If not the most, it's pretty up there. So that obviously creates a lot of challenges living in a state that has a smaller land area with a lot of these really sensitive climates, and then having some very densely populated areas. And then, of course, the environment is very important to the local culture here. And we definitely want to pay attention to this when we're making decisions about how we all live here. So this is a chart of carbon emissions per capita over time. We see with the onset of the Industrial Revolution, we have a massive increase in this. It's kind of leveled out a bit, maybe over the last 50 to 40 years or so. Could be partially due to population changes, but we see that there is this increase in CO2 emissions, which we do know has some impact on the environment around us. So this is a chart of cost of renewable power generation over time, ending in the year 2024. And so one thing we know about non-renewable sources is that they're finite in some sense. I mean, most things are finite, but we do know that there is some real uncertainty about the sources of fossil fuels. But we do know, for example, that wind is going to blow, the sun is going to shine at least for a couple billion years, so we don't really need to worry about that. And then we can see, especially with the cost of solar power and wind power, there's been a pretty marked decrease over the last 15 years or so, to the point where now renewable energy is very cost effective. So the state of Hawaii has set up the Hawaii State Energy Office to manage a lot of the decisions and research around making energy decisions for the state. So some of the tasks they're charged with is energy assurance and resilience. So making sure that we have the ability to deliver power where we need to in a robust way that's not going to be disturbed by certain outside influences, making recommendations for energy policy, making recommendations for transportation options as they relate to energy, making decisions regarding energy efficiency and understanding the best ways to promote energy efficiency, and then working with jobs and outreach related to energy. So this is a quote from the State Energy Office website. The state of Hawaii has a bold energy agenda to achieve 100% clean energy by the year 2045. Bold, but I think we're getting there. Let's see how we're doing. So this is a Sankey chart that shows energy from sources to end use and efficiency. This was made by a prior Hawai'i Data Science Institute HSEO fellow. And we see that we have a lot of room to grow in this regard. There is still a significant amount of energy that's being wasted. And the sources, we see that not that much is due to renewable at this time, but we're making progress every day. And it just shows us that we have a lot of room to grow and a lot of good opportunities out there. So what can we do to maybe steer us towards this 2045 goal? No pun intended, we have a lot of vehicles on the screen. So a couple things we can do is understand how people are using transportation options to influence the impact on the environment. We have a lot of electrical and alternative energy vehicle options. We want to see how people are interacting with the environment with transportation. So understanding when people are going around the island, when they're not, when are they charging their vehicles, how often are they charging their vehicles, how often are they, certain people use their vehicles more than other people. We also want to take a look at how certain changes in energy will impact the energy grid and how we deliver energy. If you have renewables, they're much more distributed, and you have energy kind of flowing multiple directions. So it's a little bit different way of thinking than using traditional energy sources. And then we really want to think about how we can maximize our ability to use renewables to generate the energy that we need. So doing this work does require a lot of information if we want to make good decisions, but the good news is that analyzing large amounts of data is becoming much easier. So this is a look at the number of transistors that we can fit on a microprocessor, so on a computer chip, over time from 1971 up to 2021. It follows a paradigm called Moore's Law, where about every 2 years you can double the amount of transistors you can fit on a computer chip. So the way you can think about that is the amount of computations we can actually run for a computer of a fixed size. So back in the day, you had these huge computers that could do only so many calculations. But now if you have a massive computer, you can do orders of magnitude higher calculations with the same amount of physical computer technology. You can see it's a log scale on the y-axis, so you have a 10 times increase with each horizontal line. So with this increase in computing power, we also have a lot of really cool platforms where we can do data analysis with. One of them is this platform called Databricks. So within Databricks, you can take a lot of different technology sources and uses and put them all under one roof, with structured data, unstructured data, AI, and data science, which is maybe you think about that a little bit different than traditional business intelligence. You can load and transform data in real time, and you can automate all of these processes through orchestration. So we can manage our data, train and deploy machine learning models all on one platform, which is very helpful for efficiency's sake. So if we're going to do this, we can use a couple different tools, and all of these tools exist under the hood in Databricks, so you don't need to manage all the software platforms yourself. You have MLflow, which allows you to save and retain and deploy machine learning models after you've already developed and trained them. Pandas, which is a Python library that allows you to visualize data and work with it in a tabular format. That's pretty easy. scikit-learn, a great Python library that has a bunch of built-in machine learning tools, and then Apache Spark, a distributed data analysis suite that allows you to process and store data in parallel. So one thing that we can look at is use an example problem of classifying wine by quality. So the first thing we want to do if we're trying to look at a data set of classifying wine is we can take this from the cloud and load it into Databricks. So within Databricks, this is the code to do that. This data set already existed within Databricks data sets, so it was pretty easy, but this is sort of like the code you would do to do this process. And then if you had data outside of Databricks, this top part would change, but the rest of it would stay the same. And we save it in the Databricks tabular format. So then looking at our data, we have a bunch of features, so a bunch of stuff that tells us, what information we have about a given bottle of wine. And then we have this quality score that sommeliers have probably tasted all of these wines and decided how good they think they are, going from 1 to 10. So we have one data set for red wine, one for white wine, and we want to combine those and make it into one feature. So we can take these data sets and instead of having them separate, move them into one and then add a binary label for whether a wine is red or not. And then what we want to do is instead of having like a continuous value of how good our bottle of wine is, we want to turn that into a binary measure to make binary classes of whether we call a wine quality or not. So what we do is we say if the quality has been ranked 7 or higher, we consider that a quality bottle of wine. Then we're going to split that into a set that we're going to use to train our model, and then one set that we're going to use to validate or test our model. And this is the code that you would use to do that, loading our data with Spark, doing all of the little transformations that we mentioned, and then splitting into our train and our test. So this is the one general formulation for a supervised learning problem. We have all of our data here. So this represents all of the features we have regarding our wine. And then this represents our quality label. And then this is a mathematical representation of what you're doing generally with supervised learning. You're essentially picking some machine, for lack of a better term, that takes in all the information about your wine and then spits out some label. And then you're trying to minimize how many labels you predict wrong compared to the true label. And then we pick the machine from some class of machines F that allows us to do that in the best way possible. And then for the particular model we're using, which is going to be a gradient boosting classifier, we essentially are picking these decision trees from a big bag of decision trees. And then we're trying to pick the best one that gives us that best classification of our wine. And then this function that tells us how good of a job we're doing, because it's a binary classification model, we need some certain mathematical properties. We choose this, which converts a discrete yes or no into a continuous function, which we can use all of our cool optimization tools on to solve this problem. And then this is our measure of how good of a job our model did. This is the ROC curve. I think it stands for receiving operating. I forget what the C means. It's something that came from like doing radio communications back in like World War II. But you can think of this as at different levels of where we're cutting off our classification of maybe we want to be more than 50% sure that we're classifying a quality wine as a quality wine. There's some point on here which represents that threshold level. And then we look at the number of false positives that we label versus true positives. So you could sort of think of, we want to maybe, depending on your application, find a place where we're getting kind of an even trade-off between our between how much risk we have in making a false positive versus how much more we have to gain about doing another true positive. And in our case, the area under this curve represents kind of the probability that we're doing a good job. And in this case, we got 88%. And this is the code that allows us to do that. So the Hawaii State Energy Office has chosen Databricks as its platform of choice. So these are some of the things that they're doing behind the scenes to make some of those energy decisions. Obviously, they're not using data sets with wine. They're using a bunch of various data sets, which are gathered from agencies like these. We have Hawaiian Electric, we have the Hawaii Department of Transportation, National Highway Transportation Safety Administration, and other state of Hawaii agencies. So they're taking all this data and trying to use it to make decisions like maybe, yes, we want to add solar panels here. No, we don't want to add solar panels here. So thank you very much for going on this energy journey with me. Really appreciate everyone's support. And again, for the Data Science Institute and the Energy Office for supporting this work. Thank you very much.
Hey, hello everyone. My name is Aftab, and I am the graduate fellow of the Hawaii State Energy Office and the Hawai'i Data Science Institute. At the same time, I'm doing MBA at the Shared Lab Business School. So today I'm gonna talk about some of my work and walk you through there. So let's go to see some of my work. Okay. Yeah, sorry. It was my beginning page. Okay, so the project I'm working with the Hawaii State Energy Office right now is the Haven. So Haven is the project where it is a visualization tool that helps people on decision making. So we already learned from Sam of his previous speech, like by 2045, Hawaii wants to reach net zero carbon emission by using their 100% renewable energy. But this transition is
not so much easy because Hawaii has 6 different, isolated islands, and both each of the islands has its own diversified grids and the demand needs. Also, the power plants we are using right now, we are using their oil, which is like crude oil, the lowest bottom oil, and going from there to the renewable fuel, it is a little bit difficult. To plan these transitions, the analysts and the researchers produce thousands of pages of reports, scenarios, and charts and tables. These documents are extremely complex and hard to interpret. So this is where Haven comes in. So Haven transforms these complicated data sets, energy planning outputs into a clear, interactive visualizations that are much easier for analysts and the decision makers to understand. So let's see how Haven works with a demo. So the Haven front-end dashboard is built using a React web application. So when you open the app in the left side, that let you choose the scenarios. So scenarios came from the different data sets, and using those data sets, analysts made some models on that. So when you open the scenarios and generates interactive charts showing capacity, demand, land use, RPS progress, we can compare these charts, putting side by side together and understand the trade-offs. So this helps decision makers and policy makers make better choices about capacity expansion and long-term energy planning. So here is a simple data flow, how these Haven backend is working. So at the front end, we do the request to see the capacity and the demand, and that request go to the backend. So we are in the backend, we are using Amazon Amplify. That makes our architecture. So Amazon Cognito checks whether the user is authenticated. After authentications, the process goes to the API gateway. And then the gateway gives the correct route to the correct Lambda functions, and it actually take the data sets take the data from the data sets which is stored in the Redshift and the S3 bucket. So this is the bucket actually where all the data sets are stored. So Lambda function is do an important job because it queries the data from the data set, and then it processes the data and makes a JSON format and prepare the data as a JSON format. So when the JSON format reach to the front end again, it uses that JSON format and using the JavaScript plotly functions makes the chart that we requested at the beginning, like the demand capacity. Okay, so yeah, the other work I completed with the City Energy Office is address-based data integrations earlier this semester. So why do we need to integrate data from different sources? So to understand the complete energy use pattern, we need to combine information from multiple sources like the parcel data set, vehicle data sets, energy meter data sets. So these data sets came from the different agencies. They own different agencies own these different data sets. So if we want to integrate all of these data sets, we need a common identifier or a common column that can relate all of these data sets. So in our cases, we are using the address column. So the problem with the address is it is very messy, the inconsistent and incomplete. So if I elaborate the problem with the addresses, address-based matching between the data sets. If you look into the left side, the address is clean. This is the real address we should be used in our everyday life. But when it is, I found in the data sets, this is messy. Sometimes the unit is come in the beginning of the address. Sometimes there is dash missing in the house number. Sometimes unit is calling as the apartment. So based on this messy address, when we try to match between the data sets, it is not possible to match. So we need to clean these addresses first, and normalize this in a standard form. So I used the regex cleaning regex rules to clean all of these data sets. So regex or regular expression is a tool that finds pattern in the messy text and rewrites them into a consistent format. So let's look at a small demo here. So it's a simple messy address that has some couple of hashes in front of the digits. So we need to drop all of these hashes, and then 1307 is the unit number. We need to put a unit text in front of that and with a comma. So let's see. Okay. So first, this is the a small code, the regex code that is identifying, like if you find in your text or in your address which starts with the hash, and then if you find the digits, take only the digits. So $1 means what you find at the beginning inside the bracket, take that one. So when it like scan this address, it finds that it starts with the hash 1 and take only the 1 as a clean. Clean, drop the hash and take the 1. Then the next code here, it says this again, if you find again any hash, then take, and after that it is a digit, take the digits with 1, that is, I mentioned $1, and put the common unit before that. So this is the way it can regex can clean step by step all the messy addresses. Okay, so the source of the data. So we use Databricks. That Sam said. Databricks is a platform that where you can store your data. At the same time, you can query your data, also modify your data. So I work with the vehicle datasets and the personal datasets and combine them after cleaning with the regex rules. And here is the result I found. So in our data sets, there are 2 million rows of the vehicle addresses and 200K parcel addresses. And when we, after cleaning, when we attach those data sets, my, like the matching percentage of the, 91% of the vehicle address match with the parcel addresses. So it seems to me that it is a good numbers to start the analyzing. Okay, so the other work I'm also collaborating with the Plant Environment Protection Department in the CITR. I'm teaming with Dr. Daniel Jenkins and Dr. Mohsen Parevi. So they work on the IoT-based coconut Rhinoceros beetle monitoring systems. So the coconut Rhinoceros beetle is a major threat for the palm trees across the Hawaii. The classic monitoring systems, like it is like manual process to check if there is like beetle trapped or not. But if we can install a camera over there, we can take the images using a modem and send them in the cloud, and we can monitor the beetles from our home. So that's the idea. They are working on that, and they already did a lot of work on there. So my part will be the analysis with the images. Probably the next semester I will work more on this, but with the images that already captured in the traps, I can train those images with the machine learning and like get the idea how many CRB detected, and get the idea for the early warning, like if any new detections which didn't happen in the areas previously. So we can do all of these things, training with the machine learning and with these images. So hopefully I will work more on this in the next semester. So thank you so much, Data Science Institute and the Hawaii State Energy Office to fund my work. Questions, if you have any.
Hi, I'm Andrew Zilnicki. I'm going to be talking to you about personal cybersecurity. So the reason I got into this idea for presentations and research was some personal experience with people getting their identity stolen. My mother-in-law, who is a 65-year-old retired teacher, fell victim to a phishing scam sent to her email, and she typed in her bank credentials, and she ended up not losing any money, but had to change her account and her passwords, and her bank was frozen for a few weeks, which for a retired teacher, was a hassle as well. So that's one generation. And then my younger 20-year-old cousin, digital native, also fell victim to a phishing scam and got her identity stolen and did lose money and had to go through and reset, and now has to do different steps whenever she had to get one of those notices from the IRS that her identity got stolen. So two different age gaps, both fell victim to phishing scams. And I'm something that's been around since the dawn of email, yet it's still happening. Even though technology has improved, everyone here I know has multi-factor authentication through the Duo app. So everyone here is familiar with it, but people are still getting attacked and still getting their identity stolen. Why is that happening? Because people still are the main reason of it. And one of the questions I asked, people ask me is, can you just make better passwords? Okay, this isn't going to go. All right, I'm going to try it on this side. So basically, you can go and you can create a password that it's not. And now it's, hold on, sorry. So where we go? Where we go? Sorry. So this website goes, you can actually type in a different password, and it'll, if you put in a long enough password, it will say centuries to crack. Most people still, the most common passwords that were used, again, were 1, 2, 3, 4, 5, 6, admin, and password, and guest. Those are still the most common passwords, but you should be able to just go and put a longer one in. But unfortunately, that doesn't always fix all the problems. Let's see, what's about this? So the Verizon data breach investigative report 2024 still found that most data breaches involve humans, people either on their personal level or potentially a data center user. I guess there's been a lot of the insurance companies, and I think it was Fannie Mae or one of them had their identity stolen, and millions of people's identity got out because of some kind of either human element or some kind of attack. But the most common one for the IBM's X-Force Threat Intelligence Index is still phishing. While that did fall from 46% to 25% over a 2-year span, it's actually just the amount of attacks due to stronger computers and more artificial intelligence enabled attacks. The actual volume of phishing didn't really drop much, just the percentage did. So again, even though technology is proving both for defense, it's also improving for attacks as well. And the Verizon did a study. They have been doing studies for a while. They'll send out a phishing simulation to their users. And as you can see here, over time, the amount of users that would click on it and fall for it, and the ones, this number is the ones that did not click on it but reported. You can see that it's rising, which also shows that while people are becoming more aware of what a phishing attack might look like, it's also getting better because more people are falling for it at the same time. So awareness is rising for some, but some people that aren't increasing their awareness and what to look for are falling for it because it's a better quality of phishing attack. So Pew Research has been doing research over the years of what a multi-factor authentication is, so people use it. In 2016, 52% of users said they used it. You see that there's a skew for older people not using it, and more. They said it was more towards professionals that would have to use it for their work or for their bank. So they were actually a little bit higher percentage of using it. Carrier Management is actually an insurance company, that publication. So they researched in 2025 and they said that 58% use it. And Pew found that in 23, only 48% could identify what a 2-factor authentication looked like. So what does this mean? That over time, just because people are aware of it doesn't mean that they're using it anymore. Over a 10-year period, it didn't increase. Reasons why, when asked, it was either inconvenient, they forgot about it, or they didn't think that they were at risk because they're just Joe Schmo who doesn't have any money, and why would they want to get me? So, and this kind of behavior gap doesn't just apply on the personal level. The United Kingdom cybersecurity breach survey in 2024 interviewed firms. They interviewed large firms, which was 100 or more employees, unless they were a charity, and that was then put with the small firms of under 100 people. And that the larger firms, they showed that they had a 75% multi-factor authentication adoption, while the smaller ones only had 35%. But as you can see here, they measured the amount of phishing attacks, impersonations, denial of service. Didn't matter if you were a larger firm or a small firm, the attack percentage was the same. So the attackers don't care if you're big or small. They'll go after you regardless. So your behavior is what keeps you safe, not the attackers. So let's see. So another thing that often gets looked at would be social media, which is not a bank, and it skews towards younger people. So this is a better idea of what users use it on all levels, or they just use it sometimes if they're forced to use it. And that the Cybercrime Support Network, they said that only 25% of the social media platforms required it. So if you wanted to use it, it was mostly a personal choice. Although the same report also said that about 2/3 were willing to use it. But Twitter, their 2001 transparency report only showed that 2% of users actually used it. And it's now, they recently changed to where now it's only going to be available for premium customers. So across industries, it's not necessarily becoming a standard. It's only a choice. So what do we need to change to make personal security better is we need to make it a easier, normalized behavior to where it just feels frictionless. Everyone uses it. It's not a hassle. You use either passkeys or auto multi-factor authentication. You need to be able to expand digital literacy beyond just people in this room that have come into contact with digital platforms to everyday users of why it is important. Local cyber workforce, both in the day-to-day use and prevention as well, would improve it. And then also find some way to collect the data for when they use it, if they're running into an issue of why they don't want to use it, so we can better design security for people to use every single day and not resist it. So I'd like to thank the cyber infrastructure professionals ecosystem and the Hawai'i Data Science for this research. Thank you.
Can you hear me?
Yep.
Okay. Hi, my name is Derrick McLean. I'm a graduate student in ICS for the University of Manoa, and I'm coming out of Hilo. Today, I'll be talking about a project I've been working on, the social vulnerability and climate hazard effects on the islands. So, a bit of an introduction to the project. We've been creating a geospatial visualization tool. So essentially, we're making a map of the islands and using geographical data to show different types of sets of data for social vulnerability and climate hazards. So social vulnerability is the parts of the community that will be most susceptible to different types of hazards that can be caused in a variety of different ways. Some of the different types of hazards that we're kind of looking at are flooding, sea level rises, landslides, different types of storms. And all of this is going to be presented together and showing what type of people in the community are the most susceptible to what types of hazards that appear. So some of the things that we're kind of trying to answer and show for people to be able to see is what parts, where in the state needs support, depending on what type of hazards there are, who in the community is at risk of these hazards, and what can, based on different aspects, what kind of planning can be done for these hazards. So the data sources that we've been using, all of our data has been coming from Hawaiʻi GIS and the United States Census. So all of our data for climate hazards, as I previously said, like flooding, we can collect the data from the Hawaiʻi GIS and display them as visuals on the map. Other things that we've been collecting from Hawaiʻi GIS are some points of interest. So emergency services, bridges, the different hospitals, police stations, any of the services that may be able to help depending on if a hazard happens to occur and where they can get to. And then from the Census Bureau, what we've been getting is different indicators. So there's things like different types of people, ethnicity, genders, what kind of health insurance people have, and so on and so forth. And these are the people in the different parts of the map that will be able to tell who's in the most danger, depending on what's happening. So processing the data, we do have to do a little bit because the files are so large. We have different types of cleaning methods. We both have a QGIS method and a Python method. They both do the same thing, but different parts of our group have been using them together. In QGIS, we can filter out the data, well, in both of them, we can filter out the data and simplify them. We are taking out different parts of the variables that don't matter, things that don't need to really be displayed in the view. And we've also been trying to simplify the shapes. So without losing precision of the look of the shapes for the hazard files and data, we shrink down the amount of vertices that are within the points, but don't actually lose any precision. So this is kind of a look at what we do for simplifying the data. As you can see, we in the top right of the corner of the box, of a map box, we can kind of see the simplification method, simplifying by distance and map units. This is the easiest method to keep all of the type of data that we want without actually causing any harm to the shapes of the data. This is kind of a look of what we have right now. This is the kind of layout that we are using for a visual. We can generate several types of maps, clicking on the different types of, and then on each of the different maps, we can display different types of vulnerability metrics. So as you can see, right now there's like no internet, households with no computers, households total limited to like English speaking. So there's a bunch of different types of metrics that we have listed right now, and that can be shown concurrently. This is kind of a look at what I've been doing in particular is creating the different types of shapefiles and displaying them onto the map. And you can see what type of variables each of those different sections have. So we have a lot to work on for this. It's still in development. We're still adding in more types of data, so more hazards, more variety of interests and vulnerabilities. We're still kind of optimizing the code to handle these larger and bigger data sets. And we're also adding in more features, so being able to take pictures of the scientists to be able to take pictures of different maps and being able to see a table view of the different types of data and some other additional features that will be coming in the future. So I just want to thank the different groups. I do want to give a special thanks to our social scientists, the GIS workers, and the rest of our development team. for helping work on this project. Thank you.
Thanks, Aaron. Next up, we're switching gears to our 4 undergraduate student presentations. So next up, we have Kanta Saito.
Hello everyone, my name is Kanta Saito and I'm a computer science major at the University of Hawaii Manoa. My project is on developing a data standardization pipeline for evaluation of mammography in Hawaii. Before I continue, I'd like to thank my group members Wilson and Elijah, my mentors Ariana, Dr. Sadowski, and Dr. Shepard. I'd also like to thank the University of Hawaii again, and also the University of Hawaii Cancer Center. My motivation is overall improving breast cancer AI for women in Hawaii. So most breast cancer AI is developed on datasets of white women that are from the US and Europe. But in Hawaii, we are part to look at Asian American, Native Hawaiian, and Pacific Islander subgroups. My overall goal is to have this opportunity to use computer vision techniques while contributing to this project. And a table I'd like to show to you guys is a breast cancer surveillance consortium 5-year risk table. And in the first column, we have 91,308 data in this data set. And if we go down the line, this 46 means only 46% of this 91,308 are detected as high risk and later treated. As we go down the line, 10% of Filipino women are detected, 7% of Chinese women are detected, and lastly, 11% of Japanese women are detected. And we can see that this is not really good for our Asian American, Native Hawaiian, and Pacific Islander subgroups. So our data comes from the Hawaii and Pacific Islands Mammography Registry, or let's call it HIPMR. It's a prospect cohort of women, and it collects breast imaging and breast health information. It's also linked to the Hawaii Tumor Registry to identify cases. And as you see on the right, this is our fact sheet, which is like an informational pamphlet, but also a questionnaire on there. So our project overview is focusing on answering how to develop a automated pipeline for cleaning and standardizing these HIPMR mammograms. And without data cleaning, we can't verify if these tested AI models' performance difference are from the population or the image anomalies. And this overall project involves developing methods to identify these anomalies. And on the side, we're also labeling data with these anomalies. So in this slide, we have these examples. As you see on the left, these are the ones that we'll be labeling on the side. I'll explain why later. But from the middle to the right, we'll be using a computer vision to detect these types of anomalies. Oh, okay. Anyways, one specific pre-processing method that I'd like to show it to you guys is removing pectoral muscle for medial lateral oblique images. I'll call it MLO. We used CSV metadata that contains image laterality, right or left, or image view images, so we can filter out these MLO view images. On the right, we can see that this is a original image, and then we also have a bounding region, as you see on the red line. Then we detect this using pixel intensity, and finally, we remove these images by setting it to 0. One method that I developed is a small breast compression paddle detection. We start out with the ROI definition, which is a region of interest. As you see on the right, this is a bounding box, a yellow bounding box, which is around 1/3 of the image. Then we do edge detection only on the top and bottom of the image. We say that whatever the intensity is greater than 0, not black, then we can count it as our detection. Then for visual purposes, we do line fitting. On the top, for example, we have a red line on the top with intensity greater than 0. and blue on the bottom with, the same thing. We also do a corner projection. Since these small breast compression paddle is a rectangle, to define a rectangle, we want to draw a perpendicular line from the top to the bottom and vice versa, and it encompasses the whole rectangle. And lastly, to classify it, I stated that if the red and blue overlap on both sides, then it has to be a rectangle. And we can classify this object as a small breast compression pattern. On the side, we also do some data labeling. So me and my group mates, we do 3,000 mammograms for each person. We also have a concurrence reads 1,000 to make sure we're labeling this correctly. As you see on the right, this is our UI. It's really awesome. For our ongoing work, we're still in the phase of labeling the images to train a model, hopefully in the future. We might need to label more depending on how well the model performs. And we'll also need to clean up code to make sure it's deliverable and usable for other people. Our challenges, as I stated before, the reason why we label these fine artifacts is because these artifacts are too difficult to automate using just computer vision methods. And because distinguishing between these artifacts requires visual discrimination that is also prone to error in these noisy images. There's a lot of noise in these mammograms. And to address this, we'll need to manually annotate it and also build a training data set to train a deep learning model in the future. And I'd like to thank my funding sources, and thank you very much.
Aloha mai kako. My name is Ellia Borba, and I'm a natural resources and environmental management student here at UH Manoa, and I'm specializing in plant conservation and ecology. And so for the past 6 months or so, I've been working with Dr. Casey Barton, who's a botany professor here, and I've been helping with data extraction, which is part of a greater project called the High Traits Database. So I'll go into what the High Traits Database is, but first I want to give some background and significance about the project. So as we may know, Hawaii is a biodiversity hotspot. We have over 1,500 native plants, and 90% of our angiosperms are endemic. So this means that 90% of our flowering plants here are found here and nowhere else in the world, which is really awesome. And this is really caused by these steep environmental gradients found across the islands, caused by orographic rainfall, temperature, wind patterns that occur over diverse topographies and elevations. And this has really created unique biomes with localized climates that plants have adapted to. And so this also corresponds to really high biodiversity in plant form and function, also known as plant traits. So traits are really valuable to us as scientists because traits are measurable features of plants. They tell us a lot about plant form and function, so things like photosynthesis, reproductive structures, their physiology and anatomy. And this is really important because it tells us how plants work in their environment. And this corresponds to their local adaptations, their species interactions, and their overall environmental function. So trait analysis really provides a pathway for us to compare plants across species and across different environments. And as a biodiversity hotspot, there's already a really large body of published research characterizing the traits of Hawaiian plants, as well as their non-native established plants here. However, this data hasn't yet been synthesized together for a better understanding of the diversity of plant traits here in Hawaii. So this is really what the High Traits Database is. For the first time, we are bringing together trait data into a single database so that we can better understand how traits correspond to variable climates across the islands. And so we use systematic review methods and pull together from a lot of published data to extract trait data. And so our goals are really to synthesize trait diversity across variable environments to better understand trait-climate relationships and forecast performance with climate change models. And we really want to contribute to restoration planning and conservation efforts not just for the native plant species themselves, but also for the other organisms and even pollinators and people and communities who depend on these plants. Yeah, so this is kind of how we've gone about compiling the database. First, we began with really intense literature reviews. We were searching scientific databases for to find potential publications and published papers to determine whether these papers are within the scope of what we within the scope of the data that we want to extract for the high traits database. So this is kind of where my role has come in with the data extraction. So a lot of my work is extracting data from digitized tables and graphs and then entering it into templates created by my mentor Casey and the high traits team. And so our postdoc is working on merging and synthesizing all the extracted data and doing quality control checks. And we're beginning, or in the future, we're going to begin to synthesize all this data so it's publicly available and we can publish the database in the future. And so as of last month, we've extracted almost 25,000 trait means. That represents 800 different plant traits. And this covers 226 native plants as well as 146 non-native plants or species. Yeah, so that is kind of the background and where we are in the project now, but I wanted to walk us all through what my role in the high traits database has been. And so basically how we go about this is we find papers and we have created Google Sheets that are linked together. So what my kind of role and what my workload looks like is I first visit this Google Sheet called the High Traits Progress Sheet. On the left side, you can see the names of the papers, and then on the right is kind of the attributes of how the paper will fit into our database. And then so I find the paper and I look at the spreadsheet that it's connected to. And Casey has left these really helpful notes for me, highlighted in yellow, which kind of show where the data is located and what to extract from the data and what to exclude in the data set. And so kind of like the first level of data extraction is extracting data from tables within the papers. And this is fairly simple because I'm going through and inputting these numbers into our templates. But then to kind of bring it up a level of complexity is when I am extracting data from figures in published papers. And so I get to use this really helpful web-based tool called Web Plot Digitizer. And this allows me to just screenshot the figures that are in the papers, input them into Web Plot Digitizer, and I'm able to calibrate the axes and manually annotate the data points, and usually receiving things like the mean and the standard deviation. And so I'm able to, with Web Plot Digitizer, easily extract these raw data points. However, not all of the data looks like this. Much of the data presented in papers looks like this, which is really complicated. And this is why it can't really be automated. Many researchers try to pull a lot of research from across species and across different environmental gradients. So this has kind of been the learning curve and what I've had to take a lot of time trying to figure out where the data fits and how it can be utilized for our database. So this kind of leads me into my reflections of my time working for high trait or working and contributing to high traits database. Like I was kind of saying, there's so much trait data out there, and putting this together is kind of like a puzzle piece for me. My background is more so in like greenhouse and field work. So I've gotten to get a lot of valuable experience on kind of the data science side of the world and really learned how I can contribute to building a database. And since I'm a bit more familiar with some of our native plants, though it is very detail-oriented work, I find a lot of joy in getting to read some of the papers and knowing more about some of our endangered species, some of our vulnerable species, and that's really important for me. And in the future, in the next semester, I hope to continue working with Casey and working on the high traits database. As we kind of wrap up the chapter on data extraction, I really want to contribute to the synthesis of the high traits database. So mahalo everyone for listening. Thank you for the funding. And yeah, any questions?
So some of the paper you showed in 1992, and back then, we were really terrible at finding standardized formatting of data, contributing. But we're in 2025 now. Is the community starting to sort of standardize the way we report? And is it starting to smile and no. Maybe
Yes, right.
Yeah.
I think in some cases maybe, but since we're on the kind of end of data extraction, a lot of my work has been going through the papers that aren't that easy, like the one I showed you. So this is, yeah, going into older papers that are more complicated, or even ones that have had errors in them. So we kind of, yeah, maybe. Yeah. Sorry, I'm trying to, here we go, there we go. Next slide. Okay, well, hello everyone.
Hi everyone, my name is Tyler. I'm a senior computer science major, and today I'll be talking about my project ACL papers transit analysis, advised by Haohan Yuan, who specializes in NLP, or natural language processing, a field of AI that enables computers to understand human language. So our goal is to identify emerging research trends in the field of NLP. To motivate it's a landscape analysis of the fields, so we can identify different trends and relationships in the different subfields. To do this, we gathered 17,000 papers from the anthology website of the Association for Computational Language Conference for NLP and Computational Linguistics. The documents range from 2017 to 2025. And the features that we used were the concatenated title and abstract. So our methodology is to use unsupervised machine learning techniques to discover abstract semantic structures across different documents from ACL conference papers, relating different documents together by grouping frequently occurring words. The two algorithms used for topic analysis are latent Derrick allocation, or LDA, and KeyBERT. LDA is a probabilistic topic modeling algorithm that discovers hidden thematic structures in a collection of documents. It assumes that documents belong to each topic and what words are most characteristic of each topic. KeyBERT uses BERT, a transformer-based embedding, to embed documents and keywords. Words belonging to a document are then ranked based on their similarity with the document, resulting in the words that are most relevant to the document. The main difference between the two is that LDA is about discovering the topics given a corpus or a set of documents, while KeyBERT is about discovering the keywords that are most relevant to describing a document. As for the pipeline, we start off with building a JSON dataset through data crawling, which resulted in us obtaining over 200,000 total documents. We then pre-processed the dataset with pandas by dropping documents with no abstract or title, leaving us with only 17,000 papers that range from 2017 to 2025.
We then filter the data by year before running each through the two different models, LDA and Keybert. For our LDA model, it outputs the top 10 most popular topics for each year, where each topic is embedded as a vector of the probability distribution of words that belong to it. These topics are then fed into a t-distributed stochastic neighbor embedding to reduce the high dimensionality of the topic vectors into 2 dimensionals for visualization, while preserving the local structure. For Keybert, it generates the top 10 keywords of each document, where we then sum up the total occurrences of a unique keyword for each document for each year. The results of both are then fed into an LLM to help generate insights. So this is the 2025 results for our LDA model with visualization from TSNE. Some insights you can gain from this graph is that the topics 0, 1, and 3 are the bias evaluation, emotion detection, and multilingual entity detection are all around the bottom left and are seemingly related to human diversity, ethics, and sensitivity. Clustered around the center, you can see topics 2 to 8 are also related to each other, both which is knowledge hallucination and uncertainty and domain reasoning in LLMs, and factual verification, argument mining, and scientific reasoning, which are both about truth and reasoning. And you can see a small portion of topic 2, which is the green cluster, is around cluster 7, the gray cluster. Makes sense because topic 2 is about knowledge hallucination, uncertainty, and domain reasoning in LLMs. And topic 7 is multimodal benchmarking and visual reasoning, which shows that there's also part of the space is about reasoning on the upper left. For the results from Keybert, you can infer that the LLMs are the dominant paradigm in the field based solely on the top 2, which is language models and large language. From keywords 3 to 8, you can infer that they are related in the applications of LLMs, showing that the field of NLP is currently working on ensuring that LLMs are trustworthy, are generating trustworthy information instead of hallucinations, improving their multilingual and multimodal capabilities and their reasoning. As for the overall trends, some inferences gathered from the data are the rise of LLMs and prompt engineering based on these topics from 2021 to 2025. You also have multimodal functionality for these topics such as the multimodal event extraction and visual reasoning to multimodal benchmarking and visual reasoning. It shows a shift in focus from human judgment, fairness metrics, and psychological framing, which are increasingly integrated into LLM evaluation. Next, we have bias, fairness. Oh, sorry, that was about the bias and fairness. Next, lastly, we have domain specialization, where topics like clinical NLP, scientific reasoning, and domain-specific knowledge extraction show growing interest in specialized applications of LLMs alongside the popularity of LLMs. So for the takeaway is that our pipeline for threat analysis allows us to gain insights into developing trends in the field of NLP and learn about the relationships of the subfields. It also tells us that large language models are the dominant paradigm in NLP, with research increasingly focused on accessibility, trustworthiness, and expanding their capabilities with reasoning. some challenges faced are an uneven distribution of documents for each year, or papers from conferences before 2017 usually did not have an abstract or a title, which is why they had to be removed. And there's way more papers from 2025 than 2017. That's about 10 times difference. There's also data crawling requires a lot of tuning to the specific website to get the correct data, since every website has a different HTML structure. And results might have lost some of the original patterns of the data due to the use of more lightweight models to reduce the runtime, meaning it was limited by the computation given the large data set. Lastly, I'd like to acknowledge the Change High Research Infrastructure Improvement Award by Change Hawaiʻi and the NSF. Thank you.
Hello, everyone. My name is Lionel. Thank you all for staying and just being here. And today I'm presenting an AI for academic peer review, where I basically leveraged 2016 through 2025 ICLR data to build a machine learning corpus, or just extract enough data to identify statistical analysis for AI generated review detection. Before I begin, I'd like to just say thank you to the Change Hawaii program, the NSF, the Hawai'i Data Science, and finally the University of Hawaii for allowing this research, allowing me to dive into this research and really learn a lot. And here's an overview of what I'll be going over today. We'll start off with the research question hypothesis, which includes my motivation, the theory behind this, the data set preparation that I did, my methodologies, my results, the broader impacts, and finally the conclusion. Starting off with our motivation. So as we know, ChatGPT launched on November 2022, and right when it launched, in just about 2 months, it immediately had 100 million users. And so with that background knowledge, we're trying to answer the question, how has ChatGPT's release impacted the prevalence of AI-generated content in academic peer review, and can we reliably measure this change? And so our hypothesis begins by looking at ICLR conference data. We can infer that AI-generated content in peer reviews, again, we're using just the ICLR conference data to make this inference across all peer reviews. If it would show an increase of less than 2% before ChatGPT, then we would infer that it would have increased by 10% or greater than 10% after its release, which is 2023 to 2025. And this would be detectable through statistical differences in word frequency distributions. So here's the theory behind word frequency distributions based on my research prior to this study, or based on the studies that I've looked at. We've discovered that AI and human text have different word frequency distributions. And so we decided to go for a large scale statistical analysis, which means that we will be looking at this formula where QT is our pure human baseline. This is pre-ChatGPT, RT being our pure AI baseline. So these will be AI generated completely by large language models. For this one, I chose GPT models. So these are synthetic reviews. And finally, our target corpus, which we will analyze, which will be the individual years. And again, our goal here is to analyze each year against these same baselines, this formula, and see how alpha evolves over time, alpha being the percentage of AI generated content. And so this is how we prepared our ICLR review data. we used an API provided by OpenReview, and after scraping their papers, the reviews, and metadata, after filtering, we just extracted, because we really only care about the peer reviews, right? These are the people that write the reviews to accept, decline these workshops, these papers that get submitted. And so after filtering by year, we have 198 in 2016, and we can see by 2025, we have 76,000 reviews. Again, we want to split that by pre-GPT and post-GPT. That's before 2022. We're left with 40,000, and then the rest after 2023. So overall, we have about 171,000 peer reviews, totaling up to about 2,119,000 sentences after tokenization. So here's the methodology behind this. So again, this study of the large-scale statistical framework, we referred to Liang's paper, where we officially cloned their official GitHub repo, looked at their code and imported their exact tokenization functions, used their maximum likelihood estimate inference engine, and then finally applied 1,000 iterations on Bootstrap and 95% confidence interval, which we will get more into later. So, but here's the most critical part, the tokenization method. A lot of us, when we do tokenizations, and there's a lot of frameworks out there that help you with tokenizations, we tend to isolate a lot of stop words, which they like to call it stop words being like the, is, at, a, because they're simply just irrelevant in terms of giving context, right? So for example, when a large language model, you're trying to parse a PDF, you normally try to just give it as much context as possible with as little tokens as possible. And so we remove these stop words. For example, the word could be the model is very good at detecting AI. And the stop words would be removed, so you would just feed model, very good, detecting AI. But what we did here, or what Liang did, was he used the simple regex function, re.findAll, and whatever's in the parentheses, to keep everything in the sentence. Very simple. From a previous presentation, sometimes the truth can be very simple, right? And so from the sentence, the model is very good at detecting the AI, you keep that whole thing in your tokenization. So keeps all the stop words, removes only numeric tokens, preserves word boundaries, and finally, it preserves these subtle statistical differences because, again, we are looking at the word frequency distribution against AI and humans. So just getting a little bit more into detail with the baselines. In terms of the QT, the human baseline, we have about 595,000 sentences. For the AI baseline, we used GPT's model to generate 1,000 synthetic reviews. How we did this is we fed it a two-stage skeleton. After giving the AI context of what the paper looks like and what the actual reviewers commented on that paper, we fed all that context into an AI and generated its own synthetic reviews. And we did this 1,000 times for 1,000 different papers. And so we have 23,016 sentences. And finally, our target corpus is just basically every single year from 2016 till 2025. Okay, so now looking into the MLE with Bootstrap. So using that exact baselines, we conducted the maximum likelihood estimation to find alpha, again, to observe these word frequencies. On the right, you can see the results of different year from 2016 and 2025. And what we just really have to keep in mind here is what do these alpha, CI, lower CI, upper mean? So alpha, again, is the estimated fraction of AI-generated content. CI lower, CI upper are the confidence intervals, which we did a 95% confidence interval, meaning that we are 95% sure that the true value of this MLE is at least this high or at most this high. And then half width is just our margin error. And finally, the end sentences for each year that we analyzed, which is the total number of sentences for that specific year. And so to dive into a little bit more summarized results, which we saw already in that table. So here's a more generalized one. So post-GPT, we saw that the highest number of AI-generated content came out to about 1.5%. If we recall, my hypothesis was it would be below 2%. And so we could almost take this as if it's the baseline for our model. And our post-GPT, we saw an influx of 14.6%. That's an increase of 10x in terms of AI-generated content. here's a clearer visual of what that looks like. You can see from 2016 till 2022, like I said, that 1.5, we consider that as our baseline, almost our margin of error. And then you can just see the obvious increase after ChatGPT's release. On the left side, I also added some linguistic markers of the words that were that increased post GPT. So that these are words like intricate, which increased by 117%, pivotal by 93%, and so on. And I think it's pretty obvious that there is an exponential growth post GPT with these AI generated content. And in terms of just estimating the scale of AI usage, if in 2023 we had 28,731 reviews, we can safely assume that there are about 1,900 that were AI generated content. Again, just a better visual on the right. And finally, that just comes out to about 13,000 reviews so far with AI content post GPT. And so broader impacts is just things to keep in mind now that we have our results, right? So there's two things, obviously concerns and opportunities, starting off with quality control and expertise. Now that AI is being used, it dives into transparency in the review process. I think it's also good to know, however, that AI peer review assistants do already exist out there, which could also explain exactly why we have that influx in our AI generated detection. And this obviously opens a lot of opportunities, right? So I think I also mentioned that there was only 7,000 reviews in 2016, and then we had like 48,000 in 2025. That's because there were just simply more papers that are being submitted. And that means that these writers, these authors are also using AI to help them write and submit more papers. And so what about the reviewers? So they're also, it's also helping them have a faster review turnaround. And then it also opens up a lot of opportunity in terms of language accessibility for a lot of researchers who have English as their second language, like myself. So a lot of opportunities around that. And so to conclude, our hypothesis was confirmed. To reiterate, I hypothesized that AI content in peer reviews would increase more than 5-fold after ChatGPT, and again, be detectable through word frequency analysis based on my studies from other research. And our results exceeded that expectation because we detected a 10-fold increase, again, from 1.5 to 14.6, with a clear inflection point at ChatGPT's launch at 2023. And the method validated perfectly, again, on pre-GPT years because it showed less than 2% on AI content, because you can't have AI content before ChatGPT was released. And so by applying this Liang framework to this ICLR data, we've uncovered, again, this critical point that AI usage in academic peer review is undergoing an exponential rise with no signs of slowing down. And so to summarize, I went over these things, and that's it. Thank you all.
Waipunalau, ke aloha ia kākoa pau. My name is Tori Valdez, and I'll be presenting this project, Iola na Niu o Nēia ʻāina, coconut rhinoceros beetle damage and breeding site detection in West Hawaii. My mentor for this project was Dr. Ryan Perroy, and he is also my co-author, as well as Dr. Patricia Perez. I am a research assistant for the Spatial Data Analysis and Visualization Lab at UH Hilo. I'm also a senior in my undergrad in the Geography and Environmental Science program, as well as the Hawaiian Studies program. So first, I'd like to give my acknowledgements to the University of Guam, as well as the College of Tropical Agriculture and Human Resources at UH Manoa, as well as the NSF ESCOR and Change Hawai'i and Hawai'i Data Science for funding, as well as I'd also like to thank Janelle Sayama, Rumina King, Dan Jenkins, and Chris Kiloang for the training imagery provided that I used as training for my CRB detector that I'll get into shortly. So the purpose of this project was to help the Big Island Invasive Species Company and others in detecting CRB damage in coconut fronds, as well as finding mulch piles, which are the breeding sites for CRB, to determine infestation in West Hawaii. This project is sort of a continuation from our initial CRB detection flight over Waikoloa, which is the first place on Hawaii Island where CRB was first detected. So therefore, my research questions, well, will we be able to detect CRB damage in mulch piles in West Hawaii using imagery captured from the helicopter? And can we successfully use CRB damage convolutional neural networks detection algorithm trained on very high resolution drone imagery on coarser resolution helicopter imagery? So these are two very sobering figures provided by the Hawaii CRB response, where the picture on the left shows CRB detections on Hawaii Island between October 2023 and January 2025. It kind of shows a pretty local outbreak over Waikoloa. And then on the right, we can see a spread between just January 2025 and June 2025, where we see it drastically and very fastly spreading down the coastline with a hotspot or cluster of points right around Keauhole Airport, Kona Airport. And since we saw the very fast uptick in the spread of CRB on Hawaii Island, it prompted BISC to want to carry out another CRB detection flight over Kona Airport, all the way up through Kona Palisades and up to Makali. So as a sort of series of events for October 14th, 2025, at around 9 a.m., a helicopter flight from Kona Airport took off. And at about midday, 6,400 photos were offloaded back at the SDEV lab in UH Hilo. And then we were able, the trained researchers, me, along with my coworkers, Andrew Tabake and Olivia Jarvis, were able to manually check each of the photos for the characteristic CRB frond damage and mulch piles. This is the flight path for that day. They flew at around 500 meters, and the area covered was around 4,500 acres. And the flight took a little under 2 hours. And up in the right-hand corner, shout out to the flight crew, my coworkers, Olivia Jarvis, Andrew Meyer, as well as my mentor, Dr. Peroi, and David Okita, who's not in the picture. He was the pilot. So the processing of everything from the photos and creating a database of points and suspect CRB damage trees and mulch piles took about a week. So first, the orthomosaic of the photos from the flight was made. If you don't know what an orthomosaic is basically a huge photo that consists of a whole bunch of smaller geotag photos that were taken from the flight. They were all stitched together. And then manual inspection of each of the photos continued, and we separated each of those photos that contained possible frond damage into folders based off of confidence level, low, medium, high, and then another folder for just mulch piles. And then we brought those points of the mulch piles and coconut trees into a CRB database on ArcGIS using the geotag photo to point feature. And then we were able to also run inference on these photos using their CRB detector to see if it could automatically find any of the damage to fronds that we were also picking up manually. And then the points of the CRB damaged trees and mulch piles were shared back to BIS so they can continue with their ground truthing. So like I said, I made a CRB detector. So this is kind of how it works and how it was made. It was built off of a deep forest package, a Python package specifically designed for ecological object detection and classification in aerial imagery. It uses deep learning object detection networks to identify and delineate individual tree crowns and can also be extended for other ecological objects like birds, or in this case, CRB damage. Deep Forest comes with a pre-trained model and allows users to fine-tune it and customize it using annotations. So that's what I did. I basically used label image this software where I can go and draw boxes that looks like this on the right over the fronts that had CRB damage, and then information from those annotations went into building this model. And hopefully what came out is sort of something that looks like the left photo where those boxes are coinciding, those red boxes are coinciding with my with the ground truths. So manual inspection looked a little like this. We would have the original photo up on our screens, and then we would basically just zoom in on each of those photos, on each of the coconut trees and anywhere that looked like there was mulch piles. And then we would, if we saw a tree that had damage, we would screenshot it and copy that image into another folder, like I said, based off of the confidence levels. And then we brought those points into ArcGIS from those photos. So from that, these are the suspect mulch piles. Some of the suspect mulch piles that we saw, there was 289 suspect mulch piles. And in that, we also flagged anything that looked like planting activity that would use stuff like mulch, like this in the left image, where you can see like a side by side and they're scooping up dirt or mulch into it, probably for planting. The suspect trees, we flagged 20 low confidence trees, which is something like in this circle in the green, where it could be CRB. We're not damaged, but we're not super sure. It could also be other damage, like wind damage, or it just be really close to a house, so it's rubbing. The medium confidence is, yeah, it looks a little bit more suspect. And then the high confidence is like, yeah, that's CRB damage if I ever seen it. Later on, BISC voiced their interest in having a coconut tree inventory, which is basically consists of GPS referenced georeference points of all the coconut trees in the study area, so they could include them in their long-term monitoring of the area for any increased CRB infestation. So I also ran inference on this orthomosaic to the right, using one of the lab's coconut tree models that was similarly made to like my CRB detector. And that detector was also trained on drone imagery, so it didn't do as well. But any of the boxes that it produced that had 0.5 confidence or higher, I used as sort of a guide to help me find the coconut trees in the imagery, to make it sort of go a little bit faster, the process. These points were shared as a shapefile back to BIS, so they could include these palms in their surveys. And in this inventory, there are 2,287 trees. So the results of this is the map that's generated. The brown points are the 289 mulch piles tagged, and then the green ones are the 20 low confidence suspect CRB damaged trees. There's one medium and one confidence tree in there, and then the coconut tree was inventory, which was on the previous slide, was also shared back with them. In this whole process, I learned the operation of ArcGIS Pro, and I also learned that the CRB detector needs to be improved by incorporating more annotated imagery into the training data. The CRB detector that I have is only trained on drone imageries. There's about 13,300 annotations that built up this model detector, but it's all drone imagery. So running it on a helicopter imagery wouldn't be as good because of the resolution difference. So maybe even making a separate detector using helicopter imagery might be useful for the future. And at this point in time, manual inspection is still necessary for these flights for detecting CRB damage and mulch piles. And we could also make another model using just the mulch piles for their breeding site identifications with BISC. And I realize and continue to learn the usefulness of remote sensing and field surveying to detect and combat invasive species and restore native ecosystems, especially for native and Hawaiian food crops. Mahalo.
Thank you, Tori.
Hi, can you guys see my screen?
Yes.
The full thing, yeah?
You want to try to slideshow? That looks impressive.
Oh, it might be.
You have to share that one with specific, so those slides show first and then share that also.
And just to do the slide from first and then the Zoom sheets.
Shoot. Okay, I was just trying to do that, but I don't know if that will work, so I might just try to download it fast.
Take a break here. I'll
Okay, so my name is Fiona Ryan. I am a senior in marine science at the University of Hawaii at Hilo, and I'm working with the Mega Lab and have been for the last couple of years. This semester, I've been working on a project, which is a collaborative project between the Mega Lab, the Division of Aquatic Resources, and the National Fish and Wildlife Foundation, working on conducting some structure from motion surveys in Honolulu Channel in Oahu. So the background of this project is that in May of 2021, there was a large-scale dredging incident in the channel just outside Honolulu Harbor. And what happened is this boat basically hit a bunch of live coral. It sheared lots of pieces of coral off. It upended coral. It damaged a lot of coral. And there was just a ton of damage that happened. And so a team of organizations, those 3 organizations I mentioned in my title slide, they grouped together to conduct emergency restoration, which took place from May through July of 2021. And what they did, this emergency restoration included stabilizing and uprighting these larger coral colonies, just making sure they were upright on the benthos. They would take smaller colonies and reattach them using this like heavy kind of underwater glue epoxy type thing, reattach those to the benthos, and then remove any debris like sand or silt that had gotten on top of living coral. They would waft that or remove that from the living coral. And then the longer term goals of this project are to create 3D habitat reconstructions of reef plots and colonies, and then use these to quantify the community characteristics and 3D structures of these plots and individual colonies. And with this, they're also going to combine quantifying patterns in fish assemblages to see what the marine life was doing in and amongst these colonies. So on the right-hand side here, you can see a figure showing where all of these plots are. And they're all labeled either L, M, H, or C. And that represents low coral cover, medium coral cover, or high coral cover. And so these plots, which were haphazardly chosen, they decided to basically replant these smaller coral colonies in different areas, depending on how high the coral cover already was in that area, to see if that affected how these corals grew. And then all of the C plots, all of the C plots are just control sites. So they didn't replant any colonies there. And so what we did and what we're doing is the Mega Lab, this is mostly our realm now, and what I've been doing for the last semester, a bit longer actually, is we will go to Oahu and we will, alongside DAR, do in-field surveying. This only takes a couple days, and then the data processing takes a lot longer. But we conduct structure from motion, SFM, photogrammetry, which you can see is being conducted in the photograph on the right here. And so what we do is we take a camera, and if we're doing one of those larger 10 by 10 plots, you take a camera and you swim in this long lawnmower pattern, starting from one corner of the plot. And you take overlapping photos consistently as you swim. So it takes practice for you to get good at it. So we were doing that as the Mega Lab. And at the same time, people were conducting, or actually right before, people were conducting fish surveys of the exact same plot. And then we would do the 10 by 10 plots using that lawnmower style of SFM. And then individual colonies, so those colonies I mentioned that had been replanted, we would take photos in a spiral pattern going around the individual colony right to the top. And so we would finish our field day having lots of fish counts and then tons of photos. I'm so sorry. The dogs have just started barking. I don't know if you could hear that. I can stop in a sec. But we would have these tons of photos for the full plots and then individual colony photos for the individual colonies. And then we would take all of those photos back to the lab and we would create these models. So we would upload all of these photos into Agisoft. And for both the larger 10 by 10 plots and also the individual tagged colonies, you would follow these steps. So you would align all those photos. That includes making sure that for example, if you have one photo and then you take the next photo, you want to make sure about 70% of those two photos are overlapped so that the software can pick up points that are existing in both photos and sort of stitch them together. Then we would build a point cloud using all of this data, and then you could build a model and finally build the texture. And so at that point, you have a beautiful 3D model, but you have no way of sort of quantifying lengths and area. And so for all of our 10 by 10 models, and then also all of our individual colony models, we would always place scale bars. And the use of these scale bars meant that we could build orthomosaics and digital elevation models, and then export these orthomosaics and digital elevation models to use in further analysis. With our 10 by 10s, we would take those orthomosaics and DEMs and crop them into 1 by 1 squares. And this would just give us an idea of total coral cover. And so we upload these to CoralNet in 1 by 1 sections, and CoralNet will put 50 random points per the 1 by 1 meter areas. And then you go through as an individual, so me and a couple other people in the lab, we'd go through and just assign what each point had landed on. So if it was turf, it was a different species of coral. If it was macroalgae, things like that. And so this is it gives us a general idea of what's happening within those plots. And then for the colonies themselves, we would upload them into ArcGIS and then go through and hand trace the colonies we were interested in. And then within ArcGIS, we would also be noting if there was any disease that was present, if there were multiple diseases or damage present, and how much of the coral colony that was actually taking up. And then from these individual colonies being traced, we can extract the shapefile and then use that shapefile because it's coming from the orthomosaic and DEM. We can actually extract a lot of data from that shapefile in terms of 3D metrics. And so we just collected a bunch more data in September of this year, but we've had data from 2023 to 2024. So now we have 2025, and then we're hopefully going to get a little bit more before this whole report is due sort of towards next summer. So there's still a lot more data I want to grab before I put any sort of bigger picture results. But some of the preliminary results and things that I have extracted from the data I've been working with is on the left here, you can see the different species of coral and what types of predation and diseases affect each type of coral more. So you have the 4 species of coral along the top: Montipora capitata, Montipora petula, Pocillopora meandrina, and Prydes lobata. And you can see that meandrina and lobata are being affected by a lot more different things than the other 2 species of coral. And then on the right-hand side, you get the data that I've taken from the shapefiles in ArcGIS. And this shows how much from 2023 to 2024, the 3D area of each individual colony has changed. So that red dotted line along 0 is basically no change in colony area. And then if the individual dots are above that line, that means they've grown over the year. And then you can see a couple of them have dropped down to -100. That means they've completely died from 2023 to 2024. And they're color-coded dependent on whether they were outplanted in low, medium, or high coral cover areas. So these are just a couple of the preliminary results. And hopefully going into the future and having a little bit more data, more of these interpretations can be extracted. So just looking at how outplanted colonies are growing over a long period of time, it's pretty exciting in that this is much more long-term, a long-term monitoring effort rather than just whether they survive or not. We can see which species are more susceptible to disease or sensitive to being damaged, and this is especially important after they've been outplanted, sort of to help inform which species might be a better idea to outplant in the future after an event like this. And then also how recovery rates differ according to environment, coral environment, so whether they're outplanted in a high, medium, or a low coral cover area. Mahalo. Sorry, this presentation was a little bit hectic. I had a lot of dogs running around unexpectedly, but I want to acknowledge all of these people. And yeah, thank you so much for giving me the chance to share what I've done so far.
All right. Good afternoon, everyone. Thank you all for being here today. My name is Erilyn Hacker, and I'm a marine science student at the University of Hawaii at Hilo, working with the Mega Lab under Dr. John Burns. Today, I'm excited to share my project about mapping Lalo, which is part of a broader effort to understand reef structure and ecosystem dynamics in Papahanaumokuakea Marine National Monument, one of the most remote and protected marine areas on the planet. So here's a quick overview of what I'll be talking about today. First, I just want to give a brief introduction to coral reefs, even though I'm sure we're all familiar, but why they're important ecosystems and why mapping them matters. Next, I'll talk about Lalo, an atoll in the northwestern Hawaiian Islands within Papahanaumokuakea, and I'll share what makes this site unique and why it's an important location for long-term reef monitoring. And lastly, I'm going to walk through the work that we do at the Mega Lab and how we map reefs at Lalo using structure from motion photogrammetry, what these maps can tell us, and how they help us understand changes over time. So before I get into the mapping work, I want to briefly highlight why coral reefs are so important. They are incredibly productive ecosystems. Even though they cover less than 1% of the ocean, they support about a quarter of all marine life. They also provide essential habitat, shelter, and feeding grounds for fish and countless other organisms. You can see from these images how complex the reef structure is, and that complexity creates space for biodiversity. And beyond ecology, reefs play a huge role in coastal protection. Their structure helps break wave energy before it reaches shore, which reduces erosion and protects coastal communities. So understanding how these reefs change over time is really important, especially in remote places like Lalo. But even though these coral reefs are super valuable, they face a number of serious threats. First, there's human impact, so things like overfishing, pollution, sedimentation, and physical damage. Even in remote places, human influence can reach reefs through marine debris or climate-driven stress. Reefs are also vulnerable to extreme events such as hurricanes and tsunamis. These can break apart coral structures and dramatically reshape the ecosystem in a very short period of time. On a global scale, we know sea level rise and ocean acidification are also major concerns. These warmer temperatures lead to coral bleaching, and increased acidity makes it harder for the corals to be able to regrow their skeletons. And finally, there are also natural interactions like predation and competition. So for example, like the crown of thorns sea star as a predator, or even shifts in algal competition can greatly affect the coral cover. And all of these threats make long-term monitoring especially important, which is why mapping reefs at places like Lalo helps us understand how these systems are changing over time. So next, moving into Lalo, also known as French Frigate Shoals. This is one of the atolls within Papahanaumokuakea, located in the northwestern Hawaiian Islands. It's home to a huge diversity of coral, fish, seabirds, and endangered species like the monk seal and green sea turtles. And because it's so far from human activity, Lalo gives us a rare opportunity to study reef ecosystems that have minimal direct human impact, but it's still vulnerable to large-scale threats like bleaching events, storms, and sea level rise. Mapping reefs at a place this remote helps us build a baseline and understands how these ecosystems are changing over time. So this slide shows one of the most dramatic examples of a change at Lalo, which it's a site called Rapture Reef. On the far left, you can see what the reef looked like in 2017. It was dominated by healthy plating corals with really complex structure and high coral cover. By 2019, after a series of bleaching events and also large storms, most of that coral structure was lost. So the reef shifts from living coral to rubble and algal covered substrate. And then in 2021, we start to see the system stabilize, but it's still dominated by dead substrate and very little coral regrowth. But by 2024 and 2025, while the reef looks a bit more flattened and maybe like some sand has started covering it and accumulating, we do see those dark patches, which is a species of branching coral known as Poeciloptera meandrina. We also have them here in the main Hawaiian Islands. So Rapture Reef is a clear example of how quickly a reef can transition from a thriving coral community to a completely different ecosystem. This is why long-term mapping is so important. It gives us a way to quantify and visualize these changes over time. So at Lalo, a lot of our work starts with field operations. That ranges from deploying small boats, planning dives, and coordinating with a larger ship's crew members. And once we're on site, we use scuba to survey the reef, collect imagery, and document the conditions that we're seeing. These photos show some of the different parts of that process, from launching dive teams to navigating the shallow reef structures and working with the crew. All this fieldwork is what makes our mapping possible and allows us to build a long-term record of reef health at a place that's incredibly difficult to access. So one of the main tools we use to study these reefs is structure from motion photogrammetry, or SFM. SFM is a technique where we take hundreds of overlapping photos across a reef area while swimming in a systematic, usually lawnmower pattern. A software called Agisoft is then able to stitch those images together to create highly detailed 3D reconstructions of the reef surface. These models capture fine-scale structure, things like coral growth, erosion, and changes in rugosity that are normally extremely hard to measure by hand and take way longer during a dive to calculate. So the two diving images here are showing you what the process looks like underwater, and then that center image is an example of the kind of high-resolution imagery that is made from these processes. Using SFM allows us to compare the same reef sites over multiple years and see exactly how they're changing. Once the maps are created, the next step is to analyze what's actually happening on the reef. So we're able to do this using a variety of platforms. One is ArcGIS, but specifically for this project, I've been using CoralNet. And here you can see an example of a processed orthomosaic on the left, and then on the right is what that small little square you're seeing looks like up close on CoralNet, because we usually break it down by a bunch of one-by-one quadrats. And each blue point represents a randomized point to classify. So for each of those points, we identify what's directly beneath it. So that can range from live coral, algae, sand, crustose coralline algae or CCA, turf algae, or something else. Over many points, this gives us quantitative data on percent cover, and it helps us track how the benthic community is changing over time. Another interesting thing about CoralNet is that also with the more plots that you're annotating, it starts building machine learning that then will give you an estimate of what it thinks is directly under it. And it's not always the most reliable, but after doing so many plots, it usually starts to pick up on the patterns and gets pretty good at figuring out what each point is. So while that data is still being processed, and when I'm not analyzing data or building models, a big part of our work with the Mega Lab is also involving outreach and education. We spend a lot of time working with local schools and community events, teaching students about coral reefs, photogrammetry, sorry, and how science is able to be used to protect our reefs. It's always exciting to see how students make these connections between the images we collect in the field and the real-world ecosystems they represent. We also participate in public events where we share our research, answer questions, and get people of all ages engaged with marine science. These interactions are really rewarding because they help bridge the gap between research and the community. And of course, we also manage our live stream camera, which allows anyone, whether that's in classrooms, in hospitals, in like an everyday office scenario, to be able to observe reef life at any time. And outreach is a really important part of this work because understanding and protecting places like Lalo isn't just about the data, it's about connecting people to these ecosystems and inspiring the next batch of young scientists. And with that, I would like to thank everyone who made this research and work possible.
Hey, Carolyn. Last but not least, we have Min Jun Han, who's working with Dr. Idris Dust.
Right, awesome. Are you able to see my screen?
Yes.
Okay, perfect. So, hello everyone. My name is Min Jun, and my presentation is on a vision-based approach to fog characterization using trail camera imagery. And I'm currently a junior CS major mentored by Dr. Sadowski and Joe Nicolo. So to give some background on this topic, so fog in the Hawaiian Islands is a very important thing because it's a crucial driver of cloud water interception, or CWI. And this is the process for which airborne water droplets are captured and deposited onto vegetation. So it's important because CWI is a very important variable in water balance models, and it's a pretty big contributor to how much water an area gets. And mountains that have more CWI have more fog, and it's a very important contributor in vegetation. And essentially, what we're trying to do is use a more cost-effective approach to both classifying and quantifying fog. Because currently at these sites, there are these things called fog gauges, which are mechanical devices used to capture fog and then also be able to detect how much liquid water is in that fog. These devices are pretty expensive and they are not very reliable. So what we were trying to do is use cameras on these sites so we can take pictures of the landscape and then determine when fog is present and possibly how much water is in that fog. And in addition, with these pictures on the right, we can see the graph. So using this model, we can potentially predict fog occurrences throughout the year. And this would be helpful for seeing when fog is most present or when it isn't. So as an overview, my mentor, Joe Nicolo, created a Python framework called Fog Vision, which was developed utilizing 44,000 trail camera images across 26 sites. And this model was quite successful, having a mean accuracy of 95.7% and AUROC of 0.99. And the research question I settled on was thinking if it was possible to use the vision model to further analyze the image of landscape and predict the amount of liquid water actually in the fog. And this turns the issue from a classification problem to a regression problem. And once again, efforts were mainly focused on three sites, Ka'ala, Nakula, and Park HQ. And as mentioned before, I use the Python framework Fog Vision. And what this does is it estimates fog probabilities throughout the day in 15-minute intervals. So it looks at a picture of the landscape and then gives us a probability for how certain it is that fog is in the image. Anything above 0.5 is fog, anything below is no fog. And then I also used scikit-learn to train regression models based on the vision data and the on-site climate data. So we were provided with two kinds of data. There were physical fog gauge data that was given to us that had fog LWC, was measured in grams per cubic meters. And this essentially comes from the fog gauge and tells us how much it detected during that one 15-minute interval. And then in addition, I also got the fog vision model results, which gave us a fog probability, which was a percentage from 0 to 1. And once again, anything above 0.5 means that there was fog. And there was NA values in both data sets, and I filtered those out during training. And then I used Pandas, NumPy, Matplotlib, and Grid Search CV for data compilation, visualization, and hyperparameter tuning. So what I found is that I began training a regression model using the binary outputs because that was what I was given at first. So essentially, I was given a huge CSV of the three sites. And if it was 0, there was no fog. If there was 1, then there was fog. And we can see that this would give pretty poor results since we aren't given like any other inputs than just 0 or 1. So later I was able to get the actual vision probabilities instead of just a binary 0 or 1. And what I did was that I did regression training on those. And since we had 15-minute intervals for each site, I aggregated those probabilities over a whole day. And then I also incorporated a weekly fog signal around each day. So it would take the 5 days before and the 5 days after, and it would use like a rolling technique to also add it to my features. And then in addition, to train the model, I implemented the humidity, air temperature, and rainfall as features. And these came from the on-site climate data that we were provided. And it was pretty useful for detecting fog because we can see that windfall and air temperature, etc., are very important for when fog is present. And then once again, optimized hyperparameters with ClickSearch CV. So the results I got was 0.75 R2 for Park HQ, 0.59 for Kaala, and 0.42 for Nakula. So these results were lower than expected. So what I did was perform agreement analysis on the three sites to determine where the model was failing. And we can see on the right side, there is a timeline of the morning. And we can see there's like small orange labels on the top left of each image, and that indicates a false positive. So the model predicted fog, but the fog gauge essentially had zero fog in it. And throughout the day, there were only two instances of when the fog gauge reported actual fog liquid water. And we can see that there's obviously fog in the images. So it seems like the fog gauge could be underperforming or possibly even missing the fog in this case. But in the bottom right image, we can see that there's all true positives, meaning the camera and the fog gauge agree. And we can see that this is arguably a less foggy night as well. So I'm not too certain as to why the gauge and the model agree on this day than the other day. So there could be some issues with the fog gauge on these two occurrences. And yeah, I concluded that the fog gauge was struggling to reliably pick up liquid water content and was failing essentially as a ground truth. And there was pretty low agreement for the Kaala site with 0.68 daytime and 0.54 nighttime. And in addition, here's a graph of the random forest model that I created, where it graphs the daily fog probability with the actual cloud liquid water content taken from the gauge. So we can see that the dots don't necessarily line up that well since the R2 score is 0.59. So there is definitely something going wrong either with the ground truth or the vision model, but I do rely more on the vision model since it does make more sense. And in addition, to look at the agreements a little better, I created confusion matrices for all three sites. And we can see that for the Kaala site on the top, that there are, as mentioned before, a lot of, I believe, false positives where the camera would detect fog, but then the gauge would detect no fog. And yeah, this would happen very often throughout the hours of 1 a.m. to 6 a.m. And then it would get a little better from 10 a.m. to 3 p.m., which is the image on the right. And then below that is an example of a site that the model performs pretty well on, which is Park HQ. We can see that it reliably picks up no fog, no fog, and then the other three quadrants are relatively good. And then, yeah, this is one of the examples of the challenges I encountered. So it was difficult to effectively determine the actual liquid water content in the images, and inaccurate fog gauge data made it hard to come to an accurate conclusion, since I use the fog gauge data as my ground truth. And these images, again, are just another few examples of obvious fog presence, but the gauge picking up no liquid water reports from the gauge. So we can see here, there's high probability for the first hour, so the first 15 minutes, but then below that, the fog gauge reports nothing until the last 2 images, where the fog has already cleared up and the model reports no fog. So to reflect, it might be better to filter out data points that are obviously failing and to pinpoint specific images that are being misclassified. So we can go in and take a closer look at some more of these examples and see if there's a pattern. And then we can note that the fog gauge isn't the best instrument since, as learned from Joel, it can be prone to lag, buffering, and since the way the fog gauge works, there has to be a sufficient amount of water in the instrument in order to properly gather data. And also, mountains with higher occurrences of fog will have lower accuracies. So Nakula and Park HQ, which both get less fog, will have better performance rates than Ka'ala. And then thank you to NSF and Change Hawaii and as well as UH for supporting my research on this program.